Hello, let's demystify the propensity score. We are in the context of real-world evidence where we often want to evaluate the association between an exposure, for example a treatment or a management, with an endpoint, which can be an event of interest such as death or cure or success of the management. In general, the groups are not comparable with each other because of the presence of confounding factors, covariables, that are distributed differently between the group, and this factor can be very numerous. Let's thus take the fictitious example of an observational study in real-world setting in which men and women aged between 35 and 85 years were followed with the presence of three comorbidities. In this case, the presence of cardiovascular disease, chronic respiratory disease, and renal failure. These individuals were exposed either to the reference treatment, called control, or to the new treatment. We wish to study the impact of the treatment on the occurrence of hospitalization. The propensity score is the probability for a given patient to receive a given treatment compared to another, given the observed covariates. In other words, it's a summary of an individual into a single variable. The problem of the presence of many covariates is therefore managed by this propensity score. A propensity score is calculated for each individual. Let's go back to our example. Let's suppose that we have estimated the propensity score of this woman in the treatment group, age 75 years, with the three comorbidities. The value obtained is 0.3. This means that this patient with her given characteristic has a 30% chance of being treated. Do not another individual can have the same propensity score but with different characteristics. The propensity score is most often estimated with a logistic regression, represented here by the trolley. In this statistical model are included all prognostic variables, all non-confounding variables found in the literature, but also all potential confounding variables. It's better to include more covariables with the risk of losing some precision in the estimate obtained, materialized here by scatter points within the target. On the other hand, omitting an important variable can lead to the introduction of bias and thus to a systematically distorted estimate. In the diagram, the measurements will be far from the center of the target. The main interest of the propensity score is to make the groups comparable between them in order to limit bias. To do this, four different methods can be used with this tool. The adjustment method and the matching method have already been discussed in other videos. The two other methods are stratification and weighting. We can check the effectiveness of the chosen method from the graphs of the propensity score distribution. From our example, this means that we will plot the values of the propensity score between 0 and 1 for each of the group before and after the application of the method. The first scenario is that we observe an overlap of the distribution before the application of the method. The individuals in each group are very similar, so the comparison is meaningful. In this context, it's possible to apply a method to make the groups comparable. It will only reinforce the homogeneity of the individuals. The opposite scenario is presented next, with disjoint distributions. The individuals of each group are strongly different. Applying in this case a method to make the groups comparable is not relevant. We stop the analysis. Finally, the last scenario is the one where there is a partial overlap of the distributions. The individuals in each group are sufficiently similar for the comparison to be meaningful. Applying a method to make the groups comparable is relevant, and we can see that the result is satisfactory. Thank you for your attention.